Okay, so good afternoon, everyone. Welcome to the NPTEL interactive session 9 for NPTEL Experimental Physics second course. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am Renalini, PMRF Research Scholar from School of Physics, University of Hyderabad. As you all know, that these interactive sessions we have every Saturday 3 to 5 p.m. where we discuss that week's lecture and the theories that have been discussed, and also we majorly actually focus on the numericals related to those things so that it can help you in solving your assignment questions for that week. Okay, so let's have last week's recap. So last week we had started with the amplitude splitting interference. We had discussed this thing, and Newton's ring theory as well as experiment we had discussed, that how depending on the gap between this in between this planar convex lens and this glass plate, depending on what kind of medium is there between this, and since the thickness also is varying from the center towards the end, we get ring interference pattern on the screen. So this was Newton's rings experiment, and this was the experiment. Then we had also discussed Michelson interferometer, where we used two mirrors, and the the interference pattern that we get, again it's in ring form, but depending on the distance between the path covered by, so we had a source and then it reflects from this half silvered glass plate to one side of the mirror, and remaining part of the light passes through it and reflects back from another mirror, and depending on the distance between these two mirrors and thus the path that these lights are commuting depends, and thus we get either dark or bright ring at the center. So this was Michelson interferometer experiment, and then we had just started discussing what is diffraction of light, which we were saying that it's the bending of light around any obstacle or aperture kind of object when that obstacle or that aperture is of the comparable wavelength, that whatever is the size of that obstacle, that should be comparable to the wavelength of light, then only this phenomenon of diffraction happens. And then here we were discussing the wave nature when diffraction happens, which is something given by Huygens principle, that each point on a wavefront, each point behaves as another secondary source of wave, and this means if this is my primary source of wave, then this is the wavefront. Every point on this wavefront, will act as a new source of waves, and thus we'll be getting wavefronts like this. And when these wavefronts from each point of this original wavefront they interfere, we get interference pattern. So this is what we have shown. This is primary wavefront. Each point of it acts as new source of wave, and thus, so basically this is the origin of this disturbance, and we only take the wavefront moving towards forward, and taking tangent to all these wavefronts we get this secondary wavelet. Okay, and then we had also discussed that we have two types of diffraction. One is Fresnel diffraction, another is Fraunhofer diffraction. So in Fraunhofer diffraction, we say that source and screen are at infinite distances. When we say they are at infinite distances, means we use a lens so that our source, when is kept at focal length of this convex lens, then it makes it parallel, and when the incident light we say is coming parallel and hitting whatever the source is, then we can say that the source is at infinite distance. So here under any kind of phenomenon that is happening under Fraunhofer diffraction, means the source and the screen are at infinite distances. That means we are talking about parallel incident rays. Okay, and the other one, which is Fresnel diffraction, which we will be discussing this time. Here either source or screen or both, either the source or the screen or both can be at finite distance with respect to the aperture, which is our source, or the aperture or the obstacle. So Fraunhofer diffraction is something like this, and as I said, we use convex lens so that we can fulfill this condition. Thus we can make our source light parallel, and thus we can say the source is at infinite distance. So this is what we do for Fraunhofer diffraction. Okay, so let's discuss more about theory of diffraction. So as I briefly mentioned that diffraction happens. Okay, let's first read what this definition here says. It says that diffraction of light is defined as bending of light around corners or any kind of obstacles such that it spreads out and illuminates areas where a shadow is expected. So if you have something like this, or usually we see if we are standing somewhere and there is a building and there is sun at behind, then we'll get shadow here of the building, right, depending on the position of the building with respect to the sun. If the sun is at the top or above, then the rays will be coming here and we will not be seeing the shadow of the building. So what we see is when the source of the light is behind, then we'll not be seeing sun rays here, and thus we'll get shadow. But what is happening under diffraction is that its situation is like this. Say here we have a slit, a very small opening, and if ray is coming, we expect that it should directly pass, and light we should see on the screen only in this area, only this much area, up to which whatever is the size of this opening, remaining here the portion is opaque. Okay, the screen kind of thing is kept and it has small opening, then light should pass from this, and on the screen we should see light only of the same size. But this doesn't happen. In fact, we see different kind of patterns here that we'll be discussing soon. What that means is the light, instead of going straight, it's bending away from that straight path to this sides. That is where we were expecting shadow or absence of light is going towards that side. So this is what we are calling bending of light around the corners of this slit or opening, such that it spreads out and lights up the areas where we usually expect shadow. In general, it is hard to separate diffraction from interference. This we will see. So here this definition is right, but this situation only happens when the wavelength is comparable to the size of the obstacle, or like the opening here. If I call it x, the slit opening is of x length unit, then if the wavelength is comparable, then only we will see diffraction. Otherwise, see this sun and building kind of thing, their wavelengths are not comparable. That's why diffraction is not happening and the light is getting obstructed. Otherwise, if they are of comparable wavelength, then the light will bend through this building or this big obstacle and we will not be getting shadow. But still we see this kind of situation in nature as well, the diffraction phenomena, like the silver lining which we see in the sky around the clouds, that is as a result of diffraction of light, and this happens when sunlight passes through the cloud and it bends through the edges of the cloud. Okay, as a result of this we see silver lining in the cloud. So this is where we see in nature. Okay, I hope the diffraction thing is clear now. Okay, let's move to understanding single slit diffraction phenomena. So before this we had seen Young's double slit experiment. In Young's double slit experiment we had seen we had one source, and for interference we know we were talking about that we need two sources to give constructive or destructive interference to get the uh, bright and dark alternative fringes. And for that, one important condition was to have coherent sources, and that's why we were, and getting coherent sources from two independent sources, as we said, is not easy. So that's why we were taking single source, and then we were putting two openings like this, so that we can get two sources of light which will eventually interfere to give us interference pattern. But here the we were have we but we will be able to ensure that these two sources are coherent because the origin is from the single source. So what was happening here, that it's okay. So what was happening here was that we had two different sources which were interacting, and as a result we were getting bright fringe and minima and maxima condition, right? And they were at equal distance also. Now here what we are doing, instead of taking those two slits, we have only one slit, that is one opening, and then again we have incident light. This is parallel wavefront of that light, and the opening length is A, and the light is passing through this. Again, important thing that we have to keep in mind here, we are assuming this wavelength of this light is comparable to this opening, then only the light will bend, otherwise it's supposed to go straight. But now it will bend, and say it bends at angle theta from its original path. So this was the wavefront, it was going like this. Now it's deviating or bending by theta angle. This is the center, but it's bending by angle theta, and on the screen, instead of reaching at O point, it's reaching P, say, okay. And so here we observe bending phenomenon of light or diffraction that causes light from coherent source to interfere with itself and produce a distinctive pattern on screen called diffraction pattern. Okay, so one thing more, diffraction is evident when sources are small enough. As I have been telling, that diffraction is evident and happens when sources are small enough that they are relatively the size of wavelength of light. This is very important condition for diffraction. As for interference, we were talking about the source being coherent, and also that we will get better interference fringe, that better contrast when the amplitude is similar. So here for diffraction, the very important condition is the obstacle or the aperture size to be relative of the size of the wavelength that we are using to get this diffraction pattern. So we can see this here, that let's show this diagram. Okay, maybe I did not keep this. Okay, this we can see here. So what's happening is, this was just I was telling diffraction here, but so here two things we are seeing. If the gap is narrow means it should be of size, comparable size of wavelength. If the gap is of comparable size of the wavelength of incident light, then the light will bend and we will see diffraction. If the size of the slit is wider or even smaller, then the light will not bend and it will go almost directly. And maybe it's still better comparable, that's why we are seeing some diffraction, but it will be small. So if the closer it is to the value of wavelength, the better diffraction we will see. As you can see here, the bending is more. Here the bending is very slight. So when the aperture is wider than the size of wavelength, we will get small diffraction effect, and when it's narrow and close to the wavelength, then we will get large diffraction effect. Okay. Now let's see what is the condition. As for interference, we were finding out the condition for obtaining minima and maxima and the positions. So here also we will try to get the conditions for maxima and minima of these diffraction patterns. So here A is the aperture gap. B is the, again, this is our slit or the source we can call it for diffraction, and this is the screen on which we are going to see the diffraction pattern. The distance between them is capital D, and theta, again, what is, it's the deviation of this light, how much it's bending, so that is theta. Now if we consider that here a lot of light points will be there, we will be considering for discussion right now the wave fronts or the light rays which are bending at theta angle and parallel to each other. There will be many here. If I show the one, say if this is the gap, then there will be many bending, many parallel one. Some will be bending at theta angle, lot of will be bending at angle theta and will be parallel to each other. There will be many such which will be bending at say phi angle and will be parallel to each other. So from this we will get one set, from this we will get one set, and then as a result we see the patterns that we will see what will we obtain. So here we are considering, out of all those, we are considering these three rays which are at distance of, so A was the distance of this gap. Now we are considering those three rays which are at distance of A by 2 from each other. This is special situation. We will see what it gives as final, what we get from it. So here one light is bending at angle theta, another parallel to it we are taking from the center, and another one again from this edge. So that means they are at a distance of A by 2 from each other. Now here what we see, if we have a, I said that we have light which is bending at theta angle and reaching the screen, say this is the screen, it's bending by theta angle and reaching the screen. Now if I draw, let me again draw here somewhere. Okay, this is the slit, this is one light, in parallel to it I am taking, let me just use the eraser. Okay. I'm just making it wider so that we can see the figure clearly. Say if this is at A by 2 and is parallel, then at another A by 2 we have this parallel, and they all will reach the screen. Okay, so what I'm saying is, if from the center this is deviating at angle theta and this will reach the screen, this will also is going parallel, it will also reach screen. Now I want to know what is the path difference between these two rays that I am considering. So we will drop a perpendicular here, right? So we can see this is the extra path the second ray is covering. So now how we have said that this is angle theta is, let's see this small thing. So here you see, now this is parallel to this, right? If I name these things, let me put so that it will become clear. Let's call it A, let's call it O, the center, let's call it B. Okay, let's call this B. Okay, what is happening? This one edge I am calling A, another edge I am calling B. This let me PQ. This is for our understanding. I just want to tell you how this we are getting theta when this is theta. This is it, and let's call this also. This is just the center where we expect the incident light to pass through, but it's bending from there. So, and also it helps us to know, we'll see. This is, we are taking a center, then we'll find at what position we are getting minima or maxima. From this center we measure that distance as well. Okay. So this is the thing. Now this OQ ray is parallel to BR ray, right? That means this perpendicular that I'm dropping from on this BR, it's making 90 degree. Okay, and OX, wait, let me name this also, let me call it X. So this OX is perpendicular to this. This is perpendicular to BR also, and it's perpendicular. If I extend this, I can show you that this line, since these are parallel, so this line that I am drawing, which is perpendicular to BR, is also perpendicular to this OQ line. I hope that is clear. Now, here if you see, this angle is 90 degree, right? This QOX, this angle QOX is 90 degree, and this angle QON, angle QON, which we have started and called that the light is bending by theta degree, that means this angle is theta, and the angle QOX, which is perpendicular here, that is 90 degree. Out of 90 degree, if this is theta, that means this remaining NOX will be 90 degree minus theta. Okay, this remaining thing, I don't want to highlight this because this figure is we still need, but this remaining, out of all this 90, this portion is theta, so remaining portion is 90 minus theta. Okay, now if we see angle BOX, so here this thing also is 90. Now if you see, this thing also is 90, and in this one we already said is 90 minus theta, so this will be theta, right? Let me write, or let me erase also, this gets difficult. Don't know this, oh shit, now Control Z is not working. I think this is still better. So angle NOX is 90 minus theta. Now angle BOX plus angle NOX is again 90 degree. If you see here, this OB is perpendicular to MN. OB is perpendicular to MN. That's why these two angles will again make 90 degree. NOX is 90 degree minus theta. That means this angle BOX will be 90 degree minus angle NOX. And what is this angle NOX? It is 90 degree. 90 degree minus theta. So 90 will be cancelled and we will be left with theta. So that means this angle is theta, and this angle which is parallel to it, that will also be theta. So that's how we are able to say that, where should I show, yeah, here the same thing we have. That's why we are able to say that if the light is bending with angle theta with respect to the main direction, then when these two parallel light I have and I am dropping a perpendicular, then it's also making angle theta with respect to this slit. Okay, so this was just I found it important to tell, so that you guys know how we are getting this also theta. Okay, so this you can keep in mind. Okay, now moving forward from this, so this we understood how we are getting this to be theta. Now for nth dark fringe, and if you see the lectures there, the professor has explained these things with some other kind of derivation. I think those things you can understand from there. Here I am just focusing on the qualitative understanding of this thing. So for nth dark fringe, we know the path difference if I denote by delta L. So the path difference should be odd multiple of lambda by 2, right? That means for first dark fringe, the n will be 0. For first dark fringe, delta L will be lambda by 2. Just for n is equal to 0. Okay. From this, what we see is, now this path difference, which should be lambda by 2, and also we know the path difference is, it's a by 2 sine theta a by 2 sine theta, from which we get lambda is equal to a sine theta. So this is the condition for first dark fringe. Okay, and for generalizing for nth dark fringe, the condition is a sine theta is equal to n lambda, where a is this size of aperture. Okay, fine. So we'll be using these formulas, so keep in mind. So what's happening here is that for a ray which is coming out from any point in the slit, a ray which is coming out, it will have a parallel ray at a distance of a by 2, such that they will interact and give this dark fringe. Similarly, for any light coming out from any point at length a by 4, also it will have parallel lights which will reach and give us dark fringe. So this is the meaning of this lambda is equal to a sine theta thing. Okay, now central maxima. Okay. So for central maxima, so in this pattern, we'll be getting, if I have diagram here, we'll be getting a pattern like this. This again, I think a very nice theoretical derivation is given in the lectures. From there you can understand. So what we get is a very high intensity bright fringe. This is bright fringe. Very high intensity bright fringe at the center, and then the first order maxima, and this is first order minima here. It should be completely like this. First order minima here on both sides, then first order maxima on after that, and subsequently we will see like this. But so this is also showing the same thing, that this is the aperture and this shows the intensity, this graph, and this is the diffraction pattern that we see. This is the diffraction pattern we get. There's darkness, dark fringe, bright fringe, dark fringe, bright fringe alternatively. At the center we see bright and its intensity is very, very high. This graph is showing the intensity. Okay, so what I was telling here is position of minima. If we see, so this is my slit, and we are discussing single slit. So, and this is the center, this is my screen. Now say if the light is bending and we are getting first minima at this point, let's call this point as y. From center we have to take this position. At y position from the center on both sides we will be getting this. We are getting the minima. Now since here in all these experiments, even in Young's double slit experiment, we were considering theta is very small, so that we can have a small angle approximation thing. In this small angle approximation, what we do is we consider the sine theta. Since theta is very small, we can take sine theta is equal to theta. How? Because if you remember, sine theta's Taylor expansion gives theta minus theta cube by 3 factorial plus theta 5 by 5 factorial and so on. So if theta is very small, its cube and its higher order will be even more negligible. So we just consider the first term. So that's how because the bending is not very high, as I told, we don't see the bending when we have sun ray falling on building or rock or something. That means it's very small thing. So in this, when we consider sine theta approximately equal to theta, then we get lambda is equal to a sine theta, which we can write as a theta. From this, theta will be this. Now sine theta or equal to tan theta we can take. This distance is d. Okay, when the approximation is small, we can take it as sine theta equal to tan theta, and tan theta is perpendicular upon base. So from there we will get y by d. So from here, and when I compare these two, I will get y by d is equal to lambda by a, and from this y, that is the position of the first minima, will be lambda d by a. Okay, this is important formula. Now width of, so this is the position of first minima. If I am getting like this, at the center I have maxima and then minima, maxima, same way on both sides. So this is the first minima position that I am calling y on both sides, of course. So now I got to know y is the position of first minima on both sides. That means in between them, or 2y is the central fringe which is bright. So central bright fringe width. So since y is this, that means 2y, which is the width of central fringe. Why? Because we are taking this y position from the center, from O. So 2y will be the width of central fringe, central bright fringe. So that will be 2 lambda d by a. Okay. And angular width of maxima will be angular width. So this is one point. This is another thing. Angular width of central maxima will be 2 theta, which will be 2 lambda by a. Okay. So this was with single slit diffraction. Now, so this is the kind of pattern we see with single slit diffraction. And yeah, this is the derivation that were discussed in lecture. You can see in this we were trying to find out how these intensity goes up and down. So this is the path difference we get, okay, and this is the phase difference, and then our intensity varies depends on this angle theta. Okay, now double slit diffraction, what happens is, so we have, instead of single opening, now we have double opening, something like Young's double slit experiment. Our rays are coming, since these are all under Fraunhofer, so our incident radiations are parallel. Okay, let me just check if recording is going fine. So instead of one slit, now we have two slits opening here. So how is it different is, if you again will go through all this derivation, I don't want to repeat because it's been given in detail there. So here we have to take care of two parameters. One is how much is the opening size. This let's call A. Both are of the same size, A. And what is the distance between these two openings? which we denote by D. Okay, and this between these two openings, the opaque part, you can call it B. So this A plus B is the distance between the two openings. So here the parameter A and B and D are very important. Okay, so A is the slit width, B is the opaque space between those two openings, and slit separation is D, A plus B. So here what we see is we get diffraction as well as interference. So single slit, wait a second. So in single slit diffraction, we had central bright fringe surrounded by alternating dark and bright fringe, while in double slit interference produces evenly spaced bright fringe. But another thing what happens is in single slit diffraction, we were only seeing diffraction, bending of light. Okay, but in double slit diffraction, we are seeing two things: diffraction as well as interference, since we have two uh, openings. Okay, but interesting thing is, like in Young's double slit experiment also we were talking about interference, but there we did not mention even that. In Young's double slit experiment, when we were talking last week or before that, there also we were talking about two openings and they are interacting to give interference pattern, but their diffraction was not happening. Why? Or we could ignore it because the opening was not comparable to the wavelength size. That's why we could ignore it. But if it's comparable, then two things will happen: the light passing from it, it will bend and give diffraction, and they will interact. These two these light coming from these two slits will interact and give interference as well. So here two things are happening, and as a result we'll be seeing this kind of thing. Yeah, so there will be interference pattern. Interference, we know they were of same intensity and of equal distance. So here there is overlap between interference and diffraction, and thus as a result we see something like this, that this one diffraction maxima has many interference fringes under it. This is the second diffraction maxima which has many interference fringes under it. This green overlap is diffraction fringe, and this red one is interference fringe. So each diffraction pattern has many interference pattern under it. Okay, this is the basic outcome of double slit diffraction, and the derivation you can understand from the lecture videos. So sine square beta by beta square factor is for single slit effect, cos square gamma factor for interference. And okay, and from Rayleigh criteria we can find out resolving power of grating using this formula. These things are there. Okay, after this there was something known as, so as we were discussing till now, when we discussed single slit experiment, double slit experiment, if you paid attention, we were using parallel wavefront of the incident light, because we are considering this is example of Fraunhofer diffraction, means where the screen or the source are at infinite distance. That's why what we are getting is parallel source of parallel wavefront. Even in double slit and single slit, we were considering parallel wavefronts because our source and screen were at infinite distance. Now we will discuss Fresnel diffraction, where either the source of light or the screen or both are at finite distances. They are at finite distance. Thus here our source or the incident light does not have plane wavefront, but it's something like this, as you can see, because it is at finite distance. So this is our primary wave And since from Huygens principle we know each point on this wavefront is source of another another disturbance or another wavefront, and this we get gives us secondary wavelet. Now these when reaches we get something known as Fresnel diffraction. So again here we are showing that each wavefront of primary wave, each point on it will give another, will be acting as another source of wave every point, and then when we will take tangent of all these things we will get this secondary wavelet. Okay, now there is something important parameter we need to understand, which is obliquity factor. Okay, denoted by k theta, and formula is half of 1 plus cos theta. So what is this? So obliquity factor in optics, when we are talking about in context of wave optics and Huygens principle, obliquity factor is a term that describes the intensity of secondary waves emitted by a point on a wavefront. So we are talking about intensity of these secondary waves. Intensity of these secondary waves which are coming out emitted from point on primary wavefront, and it's dependent on the angle between the direction of propagation and the wavefront tangent theta. It's proportional to this obliquity factor is dependent on theta, which is the angle between the direction of propagation. So this is the direction of propagation and the tangent, like at this point the tangent is this, at this point the tangent, at this point the tangent is this. Okay, so it is dependent on theta and is proportional to 1 plus cos theta, where theta is the angle between original wavefront normal and secondary wavefront normal. Okay, so this is known as obliquity factor. Secondary wavelets are emitted in all directions from point, but experimentally we do not consider the reverse one. It's not found. So only moving at the front, only that we consider, and we take tangent of it to get secondary wavelet. So under Fresnel diffraction, if we consider different type of apertures, we get interesting patterns. Like if we have circular aperture, instead of just slit opening, if I use a circular opening like this, then on screen we'll be getting dark, bright, dark, bright. So this is dark, bright fringes. Okay, and to explain this, Fresnel himself had explained something known as Fresnel zones, that we'll see. Its the detail is given in the again video very nicely, but we'll just briefly discuss it again here before we use all these concepts in the numericals today to solve the things. And another, so here at the center we should expect that we should get a bright spot, because the light can directly come from here and hit the screen, but instead, depending on the distance between this circular aperture and screen, we may be obtaining either at the center the dark or bright fringe. Whereas if my obstacle is circular, that here I had a opaque screen and at the center I had a circular opening. Now if my circular obstacle is like a disc, that this disc or the circular thing is opaque, and the light coming from here is bending and giving me again dark bright fringe, but here at the center I am getting bright fringe, which is strange if we think normally, because there is no light coming from here, right? Then why I am getting at the center like this? So all this is happening because diffraction is taking place, bending of light. That's why we are getting a bright fringe even though the light is not coming directly. So okay, so Fresnel half period zone, we understand that when we are talking about a circular opening, we are getting circular wavefront. So this we usually show in line, but if you imagine a sphere in 3D and you cut it out small portion, then it will be curved, right? That is what we call that if I polish the outside side, it will be a concave mirror. So something like that. That is, we can say, is the light that is coming out will have a wavefront, spheric. The light coming out from this aperture will have a, because if it's like this, it's only bending in this direction, okay? But if it's circular opening, then something like this, then the light is bending in all possible directions, right? Light is bending in all possible directions. That means instead of getting linear wavefront, we are getting circular wavefront. That's what I'm trying to explain. So we'll be getting a circular arc wavefront. And then from this, what Fresnel half period zone means is that if P is some point on the screen, okay, and this is the center, this is the at the distance B from this point on the screen, then since it's an arc, it's not a plane, right? It's not a plane, it's arced like this. So here the distance is minimum from the screen P. O I'm talking about. The distance is minimum, which is B. Now the another part, say S1, another point S1, another point S2. Here you can see if this distance was B, then this distance is little more than B. This distance is even more than B. So what is this distance? That is actually this B plus lambda by 2. Then the next one will be B plus lambda by 2 plus lambda by 2. That is 2 lambda by 2. Then next one will be B plus 3 lambda by 2. So every other point on these half period zones are at a lambda by 2 more path difference, that is at a phase difference of pi, and that's why these rings are called half period zones. Zone is between this one circle and another circle, the area is one zone, then another area that we see is another zone, and they are at a distance of half wavelength more, okay? So this are the half period zones, and when we do further more calculations and derivations, these details are well given there in the lectures, so I don't feel like we should be repeating it here because we need to focus on numericals. So these derivations you can go through in the video, and we derive area of each zone, which we find out is approximately same and independent of which zone we are talking about, mth zone. And amplitude at the point P that we were talking about, this point P at the screen, what amplitude we'll be getting finally. So from first zone we'll be getting A1, then from next zone we'll be getting A2 amplitude, then third zone we'll be getting A3. But the thing is, as I was telling you, that from the center, if we are getting some distance the light is traveling, then from this zone we will be getting with a path difference of lambda by 2, so it will cancel it. Then the next one, it is at this 2 will be cancelled, so it is a path difference of lambda, so it will add on. Then next one will cancel. So because we know when path difference is lambda by 2, we get dark fringe. So that's why for the center we will get A1, then next, which is a path difference of lambda by 2, it will try to cancel the first amplitude. Then the next one will try to add, and the next one will again try to cancel. So this is why we have written the total amplitude at point P for the whole wave. We will be getting A1 minus A2, then plus A3, then again minus A4, similar up to whatever is the mth zone. If this mth zone is odd, then this again you can understand. Then the final amplitude will be A1 by 2 plus AM by 2. If M is even, then it will be A1 by 2 minus AM by 2. Now, due to obliquity factor, which is half 1 plus cos theta, this actually tells what will be the amplitude we'll be seeing at the screen. This obliquity factor that I told you, it tells how much amplitude we'll be getting. So since the amplitude, you can see here the final amplitude will be, since AM. If M is large, that means we are dividing it into many zones, then M is very large value, then amplitude of it will be very small, because this obliquity factor or the amplitude of the light depends on theta. So higher the theta is, amplitude will keep on decreasing. So this is very small value, that means the final amplitude is actually almost equal to half of the original amplitude here also. So this is what we get, that the amplitude that will reach the screen in Fresnel diffraction through using these circular apertures will be half of the original amplitude, and intensity, which is square of this amplitude, we will get intensity to be a square by 4. So this happens in Fresnel diffraction when we have source and screen at finite distances. Okay, that means so in other diffractions you were seeing where the intensity was going very high, where the intensity were going very high, here in Fresnel diffraction the intensity is half of the original thing. Okay, so this is the difference we see in diffraction pattern of Fresnel and Fraunhofer diffraction. And this is some more derivation. We consider zone plate, like if you draw these zones on 2D, okay, then these circles here will be, this is how their radius will be depending on the order. The first circle will have root 1, and unit we don't know, centimeter, millimeter, whatever it is, some length unit, but it will be proportional to this root n. Second will be root 2 times root 2, third will be root 3. So this is one thing. And then yeah, so the important thing from this is that using this zone plate concept or this spherical wavefront that we are getting, these spherical wavefronts that we are getting from circular aperture. Okay, so what we can do is, as I said, here one we are getting here, and every alternate one zone has path difference of lambda by 2. So if what we do, let the center be there, and the next one, if I make it dark, I have some kind of opening where at the center I am keeping it open, and the next one I am making dark, and again open, and the next one dark, then what will happen is, so what I am doing is, this one amplitude will come, this will not come because I am covering this. Okay, then this will come, this will not come. So ultimately I'll get A1 plus A3 plus A5, so on. That means all this subtracting of amplitude that was happening here will stop, and I will be getting A1 plus A3 plus this. That means very high intensity at the screen at P. Normally the amplitudes were getting added and subtracted, added and subtracted, so very less I was getting here, A1 by 2 I was getting here. But if I dark and then bright, and I paint again some darkness at that which is at distance of lambda by 2, then all the amplitudes remaining will be added, and I'll be getting very high intensity here. And we know a convex lens is this kind of lens which, when light comes, it focuses at that point to give very high brightness. We use this convex lens, right, to do this kind of thing. So then we get very high brightness here. So it's like, it works like a focus lens. So this is its one application. Then this was the experiment. It was discussed, single slit diffraction experiment, where we are taking one slit of this should be A, of A width of A size opening, and then here the intensity varies as function of beta, where beta is the distance of position from the center, I naught sine square beta by beta square, and beta is pi a sine theta by lambda, where a is this opening size. And single slit diffraction experiment, it was part of Fraunhofer diffraction, so that's why our wavefront is parallel. And here, so we get central maxima for minima we have this a sine theta is equal to m lambda condition where m is plus minus 1 plus minus 2, and for central maxima we get at the center the maxima at 0 position, and yeah, and we'll see for maximas we have 1.45 different kind of thing. Okay, so this is one part of the experiment. The other experiment was double slit diffraction experiment where the intensity varies. Intensity depends on alpha and beta. Beta, which depends on A, which is the opening size, and alpha consists of alpha as well, which depends on D. D means A plus B. That is the separation between these two slits. So intensity, which will be overlap of interference fringes as well as diffraction fringes. So that's why we have alpha and beta here. So this is from diffraction and this is from interference, and they overlap, and as a result we get pattern like this. So in this what happens, there will be some interference pattern which will be getting missed because of this diffraction minima here. Okay, so we have interference for interference bright fringe we have this condition, for diffraction minima we have this condition, and when both the conditions are being satisfied, that time those particular fringes go missing. Okay, when both condition for interference maxima, which is b sine theta is equal to n lambda, and diffraction minima, okay, interference may be getting maxima condition at that particular position, but if diffraction's minima is getting, condition is getting satisfied at that position, then what happens is those fringes go missing. Okay, in this condition, this is the situation, d by a is equal to n by m, where this n is the order of interference and m is the order of diffraction. In this condition, no light will be diffracted at angle theta, so nth bright interference fringe, we say interference fringe will be missing at, because interference fringe we know they are at equal distance we usually get, but diffraction fringe does not follow that, and if interference maxima falls under diffraction minima, then those interference fringes will be missing at the place of mth dark diffraction fringe. Okay, and then these are plane transmission grating thing. This we talk about. Just a minute. I just want to save everything. Okay. Yeah, everything is safe. Okay. So this diffraction grating we will discuss next time. So here till now we were talking about Fraunhofer diffraction. Here you can clearly see we are talking about incident light wavefront, which is incident lights coming in straight line and parallel. The wavefront is vertical. So here that means we are talking about the source at infinite distance. That means Fraunhofer diffraction. Another thing, in Fraunhofer diffraction, till now we were talking about single slit diffraction, double slit diffraction. So here it's like multiple slit diffraction it is. Okay. How? Because here we will have many openings. Instead of two, we will be having multiple openings of size A, and the distance between them will be D, and then we will see what we'll be seeing on the pattern. We'll get something like this comb kind of thing that we'll be discussing next time. Yeah. So now I think we can start discussing the numerical questions. And yeah, this plane transmission grating, one lecture is there next time, so we'll be discussing these next time in detail. So let's start with this Fraunhofer. Okay, so let's start with this first question. So first question is based on Fraunhofer diffraction. So here the question is, in Fraunhofer diffraction due to a narrow slit, I think here we are talking about single slit diffraction. So due to a narrow slit, a screen is placed 2 meter away from this. So that 2 meter, let's say this is the center, okay, 2 meter away from the lens, 2 meters, to obtain the diffraction pattern. If the slit width, this A slit width is 0.2 mm, and the first minima lies 5 millimeter on either side of central maxima. So in single slit diffraction, this is the example of single slit diffraction, and we know in single slit diffraction we will be getting central bright maxima like this, and we take the position of these fringes from the center, so we will be getting something like this. So yeah, so the first minima here, in the question we have been given that the first minima lies 5 millimeter on either side. First minima is at equal distance on both sides. In here, just because I am drawing by rough hand, so it's looking like shifted, but it's symmetric. Okay, so on both sides the first minima is at 5 mm distance from the center. First minima is a distance of 5 millimeter from center O. Okay, now we need to find out the wavelength of this light that we are using here. Okay, so using the condition that we know for single slit experiment, the condition for minima for diffraction minima we are talking about, not interference. Okay, so condition for minima diffraction, or I should write diffraction minima, condition for diffraction minima is 2a sin theta, a sin theta is equal to n lambda. Now where n is equal to 1, 2, plus minus 1, plus minus 2, and so on. So for first minima, which is given us here, why plus minus 1? Because we are talking about both sides. So first minima n will be 1. That means a sin theta is equal to lambda. A sin theta is equal to lambda for first minimum. From here I can find out the value of lambda, right? Now A I have. Now what will be the sin theta, because theta also we have not been given. So the small angle approximation that we have been discussing, we are using for all these phenomena, small angle phenomena. Again, what was it? That the light is bending and the bending is very small, then we can take that sin theta is equal to tan theta. Okay, and if it is equal, then tan theta we know is perpendicular upon base, and we are talking about this actually, first minima. Okay, this is the perpendicular which is known, and this is the base which is also known. So it is, let's call the first minima position to be x1, and this is b. So for first minima it will be x1 by b, otherwise it will be xn by d. So for first minima if I'm taking care of taking this approximation of small angle, then the sine theta in this formula, because this otherwise I won't know, so this sine theta I'll take as tan theta and I'll get x1 by d. So first minima if I'll consider, I'll get a x1 by d is equal to lambda. From this, a is 0.2 mm. Okay, so our answer is in an angstrom, but we have to convert everything in 1 unit. Okay, so a is 0.2 millimeter, x1 is 5 millimeter, d is 2 meters. Let's convert this also into millimeter. So 2 meter into millimeter will be 1000 millimeter, I think. Yes, so it will be 2000 millimeter. 2000 millimeter. When we calculate this thing, let me use my calculator for this. Okay. Oh. So 5 times 0.2 divided by 2000, it will be 0.0005. That means 1, 2, 3, 4. 5 times 10 to the power minus 4 millimeter. And here our answers are in angstrom, so we'll convert it into angstrom. If this was in millimeter, okay. So millimeter to meter, how much? 1000, right? So meter to millimeter we were multiplying, so this will be times 10 to the power minus 3 meters. And 1 meter is 10 to the power minus 10 angstrom. Yes. So when I'll convert it into angstrom, it will be 5 times 10 to the power minus 7. Wait. Sorry. A meter is a bigger unit. So when we convert from this to angstrom, it's 10 to the power 10 angstrom. So this, when this I've added, and when I'm converting it into, right now it's in meter, when I want to convert it into angstrom, why? Because our answers are in angstrom. So when I convert it into angstrom, it will be multiplied by 10 to the power 10 angstrom, and it will give 10 plus minus 7 means 10 to the power 3 angstrom. That means 5000 angstrom. This is the wavelength that we are using here. So B is the correct answer, option B. So it's very straightforward. Just make this diagram, write down all the values that we have been given, think which formula we should use. Here, like, we needed diffraction minima condition, and after that just some mathematics, and also keep in mind to keep the units in same unit, and then we'll get the answer. Okay, so next question, again on single slit diffraction. So question is, a single slit of width 1 mm, here the width is 1 mm, again let's draw. So this is A. It is illuminated by a light of wavelength 590 nanometer. Find the angular spread of central maximum. Oh, so on the screen we will be getting diffraction fringes. This is the center. At the center we get the central bright maxima, right? This is O position. This is the first minima and secondary maxima, so on. Find the angular spread of central maximum. So we have to find out in theta how much is this spreading. Okay. This 2 theta actually we need to find out, because we have to find out the angular spread of central maxima, till where the central maxima fringe width position is. Okay, so for this what we will do, so we need to find out this theta basically. Okay, and finally then we have to take double of it, because we need to find out this total angular spread. So again, if we start with our condition of, so this is the central bright maxima, and this is first minima, this is first minima, this is again first minima on other side, and we have to find out the angular spread between this. Okay, so again using the condition of diffraction minima, from the diffraction minima condition we know a sine theta is equal to n lambda, where n is plus minus 1 plus minus 2 and so on. For first minima n will be 1, because we have to find out the angular spread of central bright fringe. So first minima we have to basically find out the angular spread between the first minima on both sides. So we'll put n is equal to 1 here. Okay, so it will be a sine theta is equal to lambda. From this, sine theta will be lambda by a. Lambda is 590 nanometer and a is 1 millimeter. Okay, 1 millimeter, when I put it into meters, it will be 10 to the power minus 3 meters. 10 to the power minus 3 meters. Okay, this will be 590 times 10 to the power minus 6 meters, or 10 to the power minus 6. Now I need to find out theta, so I will take sine inverse of this lambda by a that I have calculated, and when I will do that, when I take sine inverse of this, now take sine inverse of 590 times 10 to the power minus 6. Okay. Then my answer will be theta will be 0.0338 degrees. Okay, so this is theta, and now I need to find out finally 2 theta, so it will be double of this. That means 2 times 0.0338, which will be 0.0676 degrees. So this is the angular spread of the central bright fringe. 0.0676. A is the correct option. Okay, now next question. Find the half angular width of central bright maxima in the front of a diffraction pattern due to slit width. This is again the case of single slit diffraction. We have a slit with a width of 10 to the power minus 4 centimeters. We have a screen. We will be getting central bright fringe, then minima, then bright fringe. Okay, and we have to find the half angular width. So in the previous question we found out the full width in the full angular width. Here we need to find out the half angular width. That means only this part. We have to find out, and the wavelength we have is 6000 angstrom. So it will be like same for, we'll use the condition, diffraction minima condition we'll use, which says a sine theta is equal to n lambda, and for first minima it will be, n will be 1, then it will be a sine theta is equal to lambda, and sine theta will be lambda by a. Lambda is 6000 angstrom, which will be 10 to the power minus 10 meters. Okay, and a is 10 to the power minus 4 centimeters, means 1 centimeter is, in meters it is 10 to the power minus 2 meters. So here it will be 10 to the power minus 2 meters. So the final answer will be 6 times 10 to the power 3, and 10 to the power minus 10 plus 4 plus 2. This will be 10 to the power minus 6, and 6 minus 10 is minus 4. That will be 6 times 3 minus 4 is minus 1, means 0.6. Now theta will be sine inverse of 0.6. Okay. Sine inverse of 0.6, which is 36.8699. 36.8699 means, if we approximate up to 2 decimal digits, then it will be 36.87 degrees. 36.87 degrees. C is the correct option here. So you see, just by using this one single formula, we are able to find out various kind of things. So similar questions you will be able to solve if you remember these basic concepts and the relevant formula. Okay, moving on to next question. So here the question says, we have diffraction pattern of a single slit of width 0.5 centimeter is found by a lens of focal length 40 centimeter. That means it's the distance between the source and the screen. Calculate the distance between the first dark and next bright fringe. We have to calculate the distance between first dark fringe. So we get something like, if we say we're getting something like, this is the center, this is the first minima, this is the first minima, this is the first bright fringe, after that next bright fringe, this is dark. Okay, we have to find out the distance between first dark, this is the first dark fringe, and the next bright fringe. We have to find out this distance basically. Along the axis of diffraction pattern on the screen, wavelength of light used is this. We have to consider a sine theta is equal to n lambda, where n is this for diffraction, and a sine theta is equal to m lambda, where m is plus minus 1.32 plus minus 2.46 for bright fringes. Okay, a is the slit width, lambda is the wavelength of light, and theta is the direction along with diffraction is happening. So here again we use our formula. So for first, we want to find out actually this position, right? This is at the center, this is some position, let's say x1. Okay, then this will, we will see, we can call it the bright fringe position, we can call it x2. We want to find out the distance between first dark fringe and the next bright fringe. That means if I find out the position x1 and the position x2, then difference of that will give me this gap. So first order diffraction minima formula. First order diffraction minimum, okay, will be given by a sine theta is equal to lambda, because n here I am taking 1, that's why. Okay, now from this sine theta will be lambda by a. Also from this approximation we know this theta is x1 by d, right? Because a small angle approximation, we can take sine theta is equal to this theta, we can take as tan theta, which will give us x1 by d. So from that, theta is also equal to x1 by d. So using this and this, we will get x1 by d is equal to lambda by a. From this, I need to find out x1, which will be lambda d by a. Now lambda is 4890 angstrom and d is 40 centimeter. 40 in meters will be 10 to the power minus 2 divided by a, which is 0.5 centimeter. Oh, everything is in centimeter. Okay, 0.5. This for time being I am converting in meters everything. I need one more. Oh. Okay, now when I calculate this thing, let's see what I get. 4890 times 40 divided by 0.5, and my answer will be 391,200, and all the exponents will be 10 to the power minus 10 and minus 2 means this will be cancelled. It will be 10 to the power minus 10 meters. That means 391,200 angstrom, and our answers are in centimeter. Okay, so from meter, if I convert into centimeter, it will be 391,200 times 10 to the power minus 10 times, this will be in centimeter, because 1 meter is 100 centimeter. Then it will be 391,200 10 to the power minus 8 centimeter, and I have to get it in, of course, in a better form, means usually we keep decimal point after first digit. Then it will be 76543, 3.91. Oh, how many decimal digit? Okay, we can go up to 2 decimal digit. 10 to the power minus 3 centimeter. So, oh, but this is not my final answer. Okay, so this is just the x1 position, that is the position of first minima. Now I need to find out the position of, now the diffraction condition for first maxima, apart from central maxima, first maxima. Diffraction condition will be a sine theta as given in the question. Okay, we have been given maximum or the bright fringe. The condition is a sine theta is equal to m lambda, where m is plus minus 1.43, and so we will take this plus minus 1.43. It will be 1.43 times lambda. From here, when I am trying to find out sine theta is equal to, and we know sine theta for this position, which we call x2, then it will be x2 by d. This sine theta 2 we can call this, or it is happening for the same theta actually. Theta is same, with the same theta we are getting maxima minima. So theta is same, and it will be x2 by d again. So when we compare these two equations, we get A x2 by d is equal to lambda. From this, when we will calculate x2, which will be lambda d by A. So again, can okay, lambda d by, okay, I forgot one thing. Here we had, sorry, times 1.43 as well, right? That's not 1. There is 1.43 also. So this lambda d by A gave us this, and now that multiplied by this 1.43 multiplied by this 3.912 times 10 to the power minus 3 centimeters. This way, when we will calculate, we will be getting, let me see, yeah, same, because this was also lambda d by A. Here only it's multiplied by 1.43. So this will become 1.43 multiplied by 3.912. It will be, x2 will be 5.59416 10 to the power minus 3 centimeters. Yes. Now we need to find out the distance between, what the question is saying, we have to find out the distance between the first minima and the next bright fringe. That means we need to find out this. The first minima is happening at x1 position, the next bright fringe is happening at x2 position from the center. That means x2 minus x1 will give me the distance that we want to calculate. So x2 minus x1 means this 5.59416 minus 3.912 multiplied by 10 to the power minus 3 centimeter. When we subtract into this minus 3.912, it will be 1.68216 10 to the power minus 3 centimeters. Here our answers are up to 3 decimal digits, so we'll restrict it up to 3 decimal digits. It will be 1.682, right? 10 to the power minus 3 centimeter. 1.682 times 10 to the power minus 3 centimeter. That is, the option A is the correct option here. Okay, I hope you understood. If you have any doubt, you can ask me. I think it's pretty clear. Okay, moving on to question number 5th. What will be the angle of diffraction for first secondary maximum due to, so we get something like this, right? This is the central maximum, this is the first secondary maximum. This is central maximum, this is the first secondary maximum. Both sides, this is minimum, and then this is first secondary maximum. This is minimum, first minimum. Okay, we have to find out the angle of diffraction from the slit, the diffraction that is happening due to diffraction at single slit of width is given 0.55 millimeter and the wavelength is 550 nanometer. Okay, again using the, where is my cursor? Okay, using the condition of, let's use the condition of, because we need to find out this angle of diffraction for first secondary maximum. Okay, So using the condition of first, secondary, maximum, we'll get A sine theta is equal to 1.43 lambda. Okay, now A is, so the theta is like this actually. This theta we need to find out. Okay, not for minimum. Anyways, so this is the formula. Now sine theta here will become 1.43 times lambda, which is 550 nanometer. We change it into meters, it will be 10 to the power minus 9. Okay, divided by A, which is 0.55 millimeter. Now again millimeter to meter, if I'll convert, it will be 10 to the power minus 3. Yeah, so the final answer will be 1.43 multiplied by 550 divided by 0.55. It will be 1430 times 10 to the power minus 6. So when I will take sine inverse of this, the theta I will get will be 0.082 degrees. So the correct answer is answer B. Okay, the sixth question is, a parallel beam of monochromatic light of wavelength 5000 angstrom is incident normally on a single slit, and the slit width is 0.001 millimeter. The light is focused by a convex lens at its focal plane. What will be the angle for first diffraction minimum? The same thing, first diffraction minimum. This is the first diffraction minimum. What will be the angle? So we need to find out this angle. Again, pretty straightforward. So for first order, here we'll use the diffraction minimum condition. Which tells us that it should satisfy A sine theta is equal to n lambda, where n is plus minus 1 plus minus 2 and so on. So for first diffraction minimum, because minimum is singular, minima is plural. First diffraction minimum, n will be 1, and we'll get A sine theta is equal to lambda. From this, sine theta will be lambda by A. Lambda is 5000 angstrom, that is 10 to the power minus 10 meters. A is 0.001 millimeter, means 10 to the power minus 3 and meters. When I will calculate this, it will be 5 times 10 to the power 3 times 10 to the power minus 10, and this will be 10 to the power minus 3, and this will be 10 to the power minus 3, means 10 to the power minus 6. In total will be 5. 6 minus 10 is minus 4, 3 minus 4 is minus 1, means 0.5. Now theta will be sine inverse of 0.5. Okay, so sine inverse of 0.5 is, wait a sec, sine inverse of 0.5 is 30 degree. Sine inverse of 0.5 is 30 degree. So option A is the correct answer. Okay, next question, question number 7. We have light of wavelength 600 nanometer, which is incident normally on a single slit of width 0.05 centimeter. Calculate the separation between two dark bands on either side of central maximum if the diffraction pattern is observed on a screen at 2 meters from the slit. This is my slit. The distance between this and the screen is 2 meters, and I have to find out separation between two dark bands on either side of central maximum. So the center, I will be getting a central maximum, and then I will get first order minimum, and I have to find out the distance between the first order minimum on both sides. So from the center we calculate, if take this as x1 and this will also be x1. So basically I have to find out 2x1, calculate the separation between two dark bands. The separation between two dark bands on either side of central maximum is this 2x1. Okay, this is clear now. So this is what I need to find out. Now for again using the first diffraction minimum condition, which is a sine theta is equal to, for first diffraction minimum and it will be 1, so it will be lambda directly. So sine theta will be lambda by a, and if I am calling it x1, we know theta will be x1 by d. How? By small angle approximation. We can take theta is equal to tan theta, which will be this x1 by d. This is right. This is theta. It will be this x1 by d. From these two things, the sine theta I can equate to theta. From this I will get x1 by d is equal to lambda by a. That means x1 will be lambda d by a, and finally I need to find out 2x1. So 2x1 from this will be 2 times lambda d by a. Okay, and what it will be, 2 times lambda, which is 600 nanometer, d which is 2 meters, and a which is 0.05 centimeter. One more slide here. Okay, so when I calculate this thing, first I'll convert all these units to same. Our answer is in meters, so I'll convert all this in meters. Then 2x1 will be 2 times, and this 600 nanometer means 600 times 10 to the power minus 9 meters. Then this is in meters, that is alright. Then 0.05 centimeter means 0.05 10 to the power minus 2 meters. Yeah, and I'll calculate this. I will get 4 times 600 divided by 0.05, just 8000 times. When I'll solve these powers, it will be 2 minus 9, that is 10 to the power minus 7 meters. Writing it in a scientific notation, 4.8 6543.8 times 10 to the power minus 3 meters. So this is the answer. That is the distance between the minimum, diffraction minima on either side. The distance between them is 4.8, or you can say the distance between them is actually the width of central bright fringe. So this distance of or the width of central bright fringe is this 4.8 times 10 to the power minus 3 meters. A is the correct option. Next question, question number 8 is, we have a slit of width Okay, the slit of width d we have illuminated by a light of wavelength 6500 angstrom. For what value of slit the first order diffraction minima occurred at 30 degree. Okay, so for what value of this slit opening first order diffraction minima, first order diffraction minimum happens at theta is equal to 30 degree. It means a sine theta is equal, n is 1 because first order, so a or d here because we are calling it d, so d times sine of 30 degree is equal to lambda, and I need to find out d. Okay, so lambda is 6500 10 to the power minus 10 meters divided by sine 30 degree. Sine, okay, where is it? Sine 30 is 0.5. And this will be 6500 divided by 0.5. 6500 divided by 0.5. 13 10 to the power minus 10 meters means 9876 3 10 to the power minus 6 meters. Okay, this much should be the size of this slit, so that at diffraction angle of 30 degree we can get first diffraction minimum. So A is the correct option. See, we have just been using this simple formula. All we need to keep in mind is how this where central fringe will form, where minima will form, what is small d, what is capital D, how the theta we have to consider. If only this picture is clear in our mind, we will be able to just use the same simple formula and calculate all the aspects. Okay, so A is the correct answer here. Now next question, ninth question. The front of a diffraction pattern of a double slit. Okay, now we are moving on to double slit. Under the illumination of, this is the lambda we are using, appears in the focal plane of a lens having a focal length of 80 cm. This is the distance between slit and screen. The center to center separation between bright interference fringes is observed to be 1.04 mm. Okay, so the pattern that we will be getting is center to center separation between bright interference fringes is observed to be 1.04 mm, and the fifth interference maximum coincides with first diffraction minimum. Determine the width of two identical slits. So these slits are like this. This is A, this is B, and the distance between these slits is A plus B. Okay, and as I had told, when this is the situation, then on the screen we get diffraction as well as interference. This is due to diffraction, and every diffraction peak has interference peak. So it's overlap of diffraction and interference. So here the center to center separation and interference peaks we know are at equal distance. So the distance between them is 1.04 millimeter. And the another thing is given is fifth interference maximum coincides with first diffraction minimum. And we have to find out the width of two identical slits. That is, we have to find out this slit width. We have to find out this A. Okay. So for maxima interference for double slit experiment, the condition for interference maxima. Keep in mind here two phenomena are happening, diffraction and interference. So for interference, we know the condition of interference maxima. It is A sine theta is equal to m lambda, where m is 0 for center and thereon. Okay. So if A is the slit separation, And from Young's double slit experiment, we know that that slit that the position difference in interference fringes from Young's double slit experiment, we know is given by d lambda by a, where this del a is the slit width and delta x is the fringe distance between the fringes. From Young's double slit experiment, we can recall this. Fringe width or fringe distance, okay, because the width used to be. So using this, we can find out a is equal to d lambda by delta x. Now d is 80 centimeter. This thing is 0.8 meters. 0.8. Lambda is 650 nanometer, means 10 to the power minus 9 meters. Now delta x, that is the fringe width, okay, between bright fringes. The distance between or separation between bright fringe means fringe width is 1.04 mm. 1.04 mm. Now mm to meter again is times 10 to the power minus 3 meters. Yeah, when I'll calculate this, I'll get 0.8 multiplied by 650 divided by 1.04 is 500, and these powers will be 10 to the power minus 6 meters. And when I'll convert it into millimeter, it will be 500. 1 meter is 1000 millimeter. So this will be 10 to the power minus 6 plus 3 millimeter. This will be 500 times 10 to the power minus 3 millimeter. That means 1, 2, 3, 0.5. Did I do correct? 0.5 millimeter. Wait. So I'm getting 0.5 millimeter is my A. Okay. And I need to find out here is separation. Determine the width of the two identical slits. Okay. So this A I have got 0.5 mm. I need one more slide. Let me just save it once. Why is it taking so much time? Okay, finally it's done. So we found out A using the interference maxima condition. Now using the diffraction minima condition. In the diffraction minimum condition, we'll get, let's call it B sin theta is equal to width of sorry, I made a mistake here. Okay, so A that I have used here, it should be the slit separation. Okay, mistake. It should be basically D, the slit separation. This is, I am calculating the slit separation using Young's double slit experiment. So it's the slit separation I am finding out. And here in diffraction minima condition, we consider the width of each field, means A I am talking about. Okay, so it will be m lambda. Now for first order it will be 1, but another thing that we have seen, that when in particular diffraction pattern there will be number of interference fringes. In that case what happens is, when we take the ratio, like in this case it was D by A, so it will be N by M. Okay, now since it was given that fifth interference maxima coincides with first diffraction minima, so with first diffraction minima, fifth bright, this is going, that means this A is A is 5, which implies that since there are this many fringes, so the width of each identical slit will be this D by 5, it will be 0.5 by 5, which will be 0.1 millimeter. So just we got confused with notations here. This will be the question number 10. We have to consider a set of two slits, each of width is 5 times 10 to the power minus 2 centimeters, separated by a distance D, which is 0.1 centimeter, illuminated by monochromatic light of wavelength 6.328 times 10 to the power minus 5 centimeter. Convex lens of focal length 10 centimeter is placed beyond the double slit arrangement. Calculate the position of interference minima inside the first diffraction minima. So here we have to find out in first diffraction, where is it? First diffraction minima. Okay, so first diffraction minima, which is coming here. In this we have to find out which interference minima is coming. We have to find out position of interference minima inside first diffraction minima. So the first diffraction minima, symmetric on both sides. We have to find out what is the position of interference minima under this diffraction minima. Okay. So for this, and how many we have? So for first we will find out the minima, first order minima position from here. Okay, so for minima diffraction, what is this? For minimum diffraction, first order minimum diffraction, condition is if B is the slit width, B sine theta is equal to n lambda, and for first it will be n is equal to 1. So sine theta will be lambda by B. Now also we know theta is equal to x1 by the D, and the D here is this focal length, that is the distance, okay, that we have been given. That means this x1 will be, from here when we calculate, so what we get is theta is equal to lambda by B and x1 by D. That means lambda by D is equal to x1 by D. That means x1 is lambda D by B. Lambda is 6.328 times 10 to the power minus 5. D is, where is the 10 centimeter, means 10 times 10 to the power minus 2 meters divided by B. B is 5 times 10 to the power minus 2 centimeters. When we'll calculate this, it's here. We'll take 3-4 slides. Okay, and I'll calculate this. 6.328 multiplied by 10 divided by 5. I will get this x1 position, that is the position of first diffraction minimum, will be 12.656, and the powers, if I do 10 to the power minus 5 and 10 to the power minus 2, it will be 7. Okay, this will be cancelled, so it will be 10 to the power minus 5. Where is it? 10 to the power minus 5 meters. Yeah, this is the position of first order diffraction minimum. Now I'll calculate this. If I write in centimeter, it will be 0. This will be in centimeter, it will be 12.656 times 10 to the power minus 5. Meter to centimeter, when I will do, it will be 1 meter is 100 centimeter. It will be 10 to the power 2 centimeters. And this will be 12.656 times 10 to the power minus 5 plus 2 minus 3 centimeter. Means 0.1266 centimeters we can consider. Okay, and this is the position of first order minimum. Now for interference minimum condition, for interference minimum from the d sine theta, it's odd integral multiple, right? So we get from double slit experiment, this is the formula we use. And for m is equal to 0, at the center we will be getting sine theta naught is equal to lambda by 2d. So x0 is the first interference minimum from central point of diffraction pattern. 0 is the first interference minimum from central point of diffraction pattern. Okay, so from here, and also since we know, we always use this also, is if we say the position is x0 and the focus or the distance that we are using d, right between the source and screen, and from these two we can equate lambda by 2d is equal to x0 by capital D. From here, if I want to calculate x0, I will get x0 is equal to lambda d by 2d. Again, the lambda here is 6.328 times 10 to the power minus 5, 6.328 times 10 to the power minus 5. Capital D is 10 centimeter, just 10 centimeter. When I convert it into meter, it will be 10 centimeter times 10 to the power minus 2 meters divided by 2 times small d. Small d is 0.1 centimeter, 0.1 centimeter, again 10 to the power minus 2 meters. When I solve this, I will get 6.328 times 10 divided by 2, 31.64 0.164, and this power will be 10 to the power minus 5. Previous speakers. 10 to the power minus 5 meters. In centimeter, it will be 1 meter is 100 centimeter. So then it will be in centimeter. And then it will be minus 3 to 0.03164 centimeter will be this is the position of first minima under the first interference minima under the first diffraction minima. So under this first diffraction minima, the first interference minima we are talking about, this is the first interference minima. Okay, so this is the one position, 0.03164 centimeter. Or wait a second, 2 minus 5 is minus 3. 1, 2, 3.0316. I think this is okay. Then next is, or did I do some mistake here again? 6.328 and 10 to the minus 5, 10 divided by, and this was all in meters, and then from meter, if I convert it into centimeter, we'll multiply it by 100. I think I did some mistake. 6.328 multiplied by 10 divided by 2 and divided by 0.1 is 316.4. I made this mistake. Okay, then it will be this. Then in millimeter it will be 0.03164 millimeter. One decimal digit problem is doing. Okay, this is the first interference minima under first diffraction minima. Now for second interference minima, then it will be sin theta 1 is equal to 3 lambda by 2d. How? 2m plus 1 lambda by 2 we had, right? For x0 we calculated by keeping m0. Now when we keep m is equal to 1, it will be 2 plus 1 lambda by 2, that is 3 lambda by 2. Okay, and then from here again sin theta 1 will be x1 by d. So from here we'll get x1 by d is equal to 3 lambda by 2d. From here x1 will be 3 lambda d by 2d. So whatever answer we got, we have to multiply it by 3. 0.03164 nm. This will be 3 times 0.03164. That is 0.09492 millimeter. This is the next interference minima under the first diffraction minima. Okay, now if I calculate for m is equal to 2, that is the third interference minima, then I will get sin theta 2 is equal to 2 times 2 plus 1 lambda by 2, that is 5 lambda by 2. This b will be here. Okay, that means sin theta 2 will be 5 lambda by 2d. Also sin theta 2, I'll get x2 by d, right? Yes, this implies x2 by d is equal to 5 lambda by 2d. From this, x2 will be 5 lambda by times d by 2d, which is 5 times lambda d by 2d, which is the 0.03164. 0.03164 millimeter. This will be 5 times 0.03164. 0.03164. This will be 0.1582 millimeter will be the position. Okay, but now we have to see one thing, that the position of first uh, x2 delta x we calculated where our diffraction, this width for diffraction minimum we calculated 0.126. This was actually our delta x. Okay, this was our delta x that we had calculated the, and now under this its value we got 0.1266. So if the width of the dark fringe was 0.1266 point, so this is in millimeter, 0.1266 millimeter, then x1 is fine, x0 is also fine, but x2, which is coming 0.1582, it's exceeding the minima fringe, so we cannot consider this. I mean, this is not under the first diffraction minima. That means under first diffraction minima we have interference minima x1 and x2, and the values are we have x0 and x1 interference minima, and the values are 0.03164 mm and 0.09492 mm. That means this, if we restrict up to only 4 decimal digit, we see is the correct answer here. So with this we finish our related to this. I hope you guys understood, and then next week we'll be starting the discussion with diffraction gratings. So if there is no doubt, I'll stop the recording and the session.